This is a really interesting concept. We're looking at how to reduce diesel consumption from a refrigeration perspective on these long-haul semi-trailers that are holding refrigerated perishables, in most cases food, sometimes vaccines. So we're going to sort of have a cursory look at how many panels we can get on a roof, should we use batteries, and how much diesel will actually save. In this training video, we'll be looking at the viability of installing solar panels on top of large refrigerated trucks that traverse our continent and many others, hauling perishables with the goal of reducing the existing diesel consumption required to keep these goods at the optimum temperature. This is an interesting one. I'm going to analyse the viability of putting solar panels on top of B-double trucks. Basically, they're called reefers, refrigerated trucks containing perishable foods, and trying to look at how we can reduce the diesel consumption. Let's get stuck into it. We'll be looking to explain the concept, size a realistic PV add-on, and show the potential business case, if any. Here we go. So here's the agenda. Can the roof power its own cooling? And the problem framing is this: the diesel spend, emissions, and the unused roof area. So what we're looking at, these semi-trailers have a big roof area, in some cases with a double trailer up to 60 square metres. Now, can we put solar on top? How much solar can we put? And how much will it contribute to reducing the diesel consumption required to keep the truck at a certain temperature? Because, by the way, we're hauling perishable goods. So we're going to look at the concept. We're looking at lightweight PV, assist on both trailers. Sizing walkthrough. We can look at the area, the kilowatt peak, the kilowatt hours, and the diesel offset. So we're going to look at the engineering compliance. In other words, the maximum height, the weight, and the wiring. Because obviously putting solar panels on top of the roof of a semi-trailer is going to increase its overall height there. And there are many height restrictions, not to mention the additional weight of the panels. We're going to look at the pros, cons, and risks, action plan, a pilot, and the KPIs. Let's start with problem framing. Reefer diesel consumption emissions are significant on these long northern corridors. So we're talking about an area, say, between Sydney and Townsville, which has got a fair amount of solar radiation. And obviously, we're working on the assumption that the solar panels that we put on these reefers will be in a purely horizontal configuration. You're talking about long sunny routes, Queensland, New South Wales, with large unused roof area. Now the aim, daytime PV assist to reduce diesel burn without compromising cold chain. In other words, we don't want to compromise the temperature that these goods must be kept at. Concept overview. Low profile PV across both trailers that feeds the reefer electrically. Options: direct assist, no battery, hybrid with a small LFP buffer or full ETRU, daylight savings, diesel remains for nights, pull down, cloud cover, and electric transport refrigeration unit is an ETRU. Baseline facts, indicative. Now, a reefer fuel draw, you're looking at anywhere between 2 to 4 litres per hour for electrical standby power, which equates to 7 to 10 kilowatt. The usable roof area, there's 2 vans, 50 to 65 metres squared after setbacks and hardware gear. PV power density, flexible. You're looking at panels of 150 to 180 watts per metre squared, so 2 to 4 kilograms per metre squared. Framed 190 to 210 watts per metre squared, and 11 to 14 kilograms per metre squared. Now, in this case, we are going to be looking at flexible panels. There's no real option from a weight perspective and also a profile perspective of looking at framed, your standard PV panel. So we are looking at flexible panels here. Low profile, very thin, and able to be adhered to the top of the truck. Solar resource. Horizontal corridor average, you're looking at 5 peak sun hours per day over the year. Rule of thumb outcome, example, 60 metres squared times 180 watts per metre squared equals approximately 10.8 kilowatt hour peak. With about 5 peak sun hours a day, you're looking at around about 38 to 47 kilowatt hours a day of PV energy being produced. Daytime assistance, not a standalone replacement for diesel in all conditions. Architecture, A. PV assist, no battery. So you're looking at PV, a maximum power point tracker or inverter, and a reefer electric standby or DC bus. Pros: lowest capex, lightweight, tangible diesel cost savings. Cons: no guarantee under clouds, pull down. Diesel remains the primary source. So that's the thing. If without that battery storage component, you are relying on the sun to reduce those loads. So we're going to add 5 to 20 kilowatt hours of battery and a bidirectional inverter in this situation. Pros: smoother operation, more hours, diesel off, supports brief stops. Cons: obviously a higher capex, more weight, and life cycle and thermal management needed. So we're talking about a bit more of a complicated system. As soon as you introduce batteries into the mix, you're talking about more complication, more monitoring, obviously more weight, and of course more costs. But you can potentially address some loads outside of daylight hours. Architecture C, full engineless ETRU. Battery electric refrigeration, PV as a range extender. Pros: max diesel elimination, quiet operation. Cons: highest capex, careful duty cycle and charging strategy for the line haul. Mounting and integration. So it's really important that the height restriction is there, because obviously you don't want to be going under a bridge and shaving those solar panels off, for want of a better expression. Let's get back to it. So the height, we're going to keep under 4.3 metres or sometimes 4.6 metres on approved routes. So we're going to prefer to use, in this case, 2 to 3 millimetre flexible laminate panels. Now the weight and the payload, you've got a target of less than or equals 250 kilos, and that's for about 60 metres square of covered roof area using the flexible panels. Fixing, bonded laminates and retained leading edges. You also have to take into consideration UV resistance and wash down. Obviously these trucks are washed down. How robust are the panels? Will the adhesive take the strain of a pressure cleaner or similar? Wiring, high voltage strings, less than or equal to 1000 volt VDC. Protected runs, DC isolators, and also quick disconnects between trailers. So you're going to remember these trailers will be separated, so the design has to take that into consideration. Mounting and integration too. Inverter, maximum power point tracker location, front machinery bay or sealed IP locker. So this is a design decision of where the actual gear is going to go, and that's very important from a space and size and weight perspective as well. Earthing, EMC, lightning, bond to the trailer earth, surge protection, and EMC separation. Cleaning and upkeep. Add non-slip walk zones, schedule quarterly cleaning. And this is the issue with putting a panel into a horizontal configuration. There's no self-cleaning, and self-cleaning in itself is a bit of a myth, but at least a panel at 10 degrees is going to actually clean itself a little bit better than something in a dead horizontal configuration. If maintenance and cleaning isn't part of the regime, you're going to get a severe reduction in output from the panels. Worked example assumptions. Usable roof area, 60 metres across 2 boxes. Flexible PV, 180 watts per square metre, and we're going to install 10.8 kilowatts. Looking at the corridor average, horizontal, you're looking at 5 peak sun hours a day and a performance ratio of 0.75. We're going to look at about 300 sunny days a year and the diesel equivalents of about approximately 0.30 litres per kilowatt hour. Daily PV, 10.8 times 5 times 0.75. So you're looking at around about 40 8.5 kilowatt hours a day. That's what it's actually going to produce on average. Annual PV, approximately 12.2 megawatt hours a year. The diesel saved is 3,660 litres a year, and that's at 0.3 litres per kilowatt hour. So it's a considerable saving of diesel. So if the reefer is consuming about 2.5 litres an hour for approximately 2,000 hours a year, you're looking at about 5,000 litres per year baseline, and the PV offsets a significant daytime share. Now, you've got to remember, as we all know about solar, even in a horizontal configuration, you're going to have less production in the early morning than you're in the late afternoon, all other things being equal. And the consumption load of a refrigerated truck is not going to vary that much during the day. A little bit at night time if they're doing a 24-hour stint, but it's going to be pretty standard during the day, take into consideration the thermal mass of the refrigeration and various other factors. If you're looking at diesel at around $2 a litre, saved per B double set, it's about 7.3K a year. Now, the PV capex flex at 10.8 kilowatt, that's the size of the array. At approximately $1.50 per watt, it's about 16K. Inverter, maximum power point tracker, switchgear and install, 12 to 15K. Let's look at the total capex as being around between 21 and 31K, and this will achieve a simple payback of 3.5 to 4.2 years, duty cycle dependent. Now, we have made a lot of assumptions, and in my next video, I'm going to delve in a little bit deeper with the numbers, and we're going to do some what-if analysis, some goal seek to see what other kind of scenarios we can come up with, varying the size of the array and the peak sun hour, the peak sun hours that we actually input as well. But in this situation, you are looking at under 4.2 year payback, which is pretty good. Let's look at the sensitivity range. At the low case, you're looking at 6.1 megawatt hours a year, and this equates to saving 1,840 litres in a year period. The high case, it's 21.5 megawatt hours a year with a little over, nearly 6,500 litres a year saved. So some of the things we have to look at are dominant drivers, diesel price, usable roof in metres squared, and hours in the daylight. Now, let's look at AC or DC refrigeration tech. A standard TRU is 400 volts, 3-phase, electric standby, fed via off-grid inverter, 10 to 20 kVA. E-drive, engineless units, exposed electric bus, PV, DC link, more efficient. No battery, viable for daytime assist only. But if you put in a small LFP buffer, 5 to 15 kilowatt hours, this can actually boost reliability. Compliance and constraints checklist. Height rules, 4.3 metres general, and sometimes you can go up to 4.6 metres on approved routes, as mentioned previously. Mass and payload. You have to look at the track axle spreads, confirm roof live load with OEM. Fire and electrical, string fusing, DC isolators, surge protection and IP enclosures. Roof integrity, very important. OEM sign-off for bonding, penetrations, washdown compatibility. In other words, you want to maintain the IP status of the actual trailers after you've actually installed the solar panels. Telematics, log fuel burn, reefer kilowatt, temp and door events. Pros, daytime diesel reduction, less idling, lower dock noise, and of course the ESG benefits. Cons, risks, intermittent generation, roof wear, added maintenance, and payload impact. Mitigations, design margins, small buffer, diesel fallback, and O&M plan. Ideally, you set up a pilot plan. And in this case, we can look at 1 to 3 representative lanes. In other words, say Townsville to Sydney or Sydney to Townsville is a pretty decent run. You look at the instrument, a control trailer, 4 to 6 weeks to baseline. A detailed roof survey, usable area, obstructions, heights and weights. Engineering design, PV tech, stringing, inverter rating, EMC, lighting. Compliance review, route heights, OEM approvals, electrical sign-off. Install the pilot kit, integrate the telematics, operate 8 to 12 weeks across season. And this will give you some pretty good data to work on. KPIs. Litres per hour reefer fuel, day versus night, percentage hours of diesel off, and PV kilowatt hour contribution. Track payload impact and maintenance tickets compared to control trailer. Tricky questions and the talking points. Can the PV run the fridge alone? That's one of the tricky questions. Often daytime steady state, that's not guaranteed under a cloud pull-down situation. So do we need batteries? Not strictly, but a small buffer does improve reliability and savings. What about hail and washdown? Obviously, as the weather events are becoming more and more extreme, the panels are in a horizontal configuration, so therefore subjected to the full perpendicular force of hailstones and hailstorms, assuming there's not too much wind. Yes, they are laminates. So how will they fare under being bombarded by hail? So it is something to ask, to take into consideration when you're doing these pilot plans. Rugged laminates, abrasion-resistant top sheets, and guarded edges. And will we breach the height? Again, we're still talking about flexible laminates, 2 to 3 millimetres, so not much room on top of the existing trailer. New steps, call to action. Free desktop pre-fit using your lane data and reefer model. If it pencils out, small pilot with measured AB against control. Deliverable verified saving report and rollout bill of materials. We hope you enjoy this brief examination of the viability of putting solar panels on top of B-double trailers, specifically to address the refrigeration units and their diesel draw. Now, always with these particular presentations, don't forget to like, comment and subscribe, and I'll see you in the next one.